Hi guys, in this video I'm going to show you guys how to write the proof for this statement right here. We're going to be using the method of proof by contraposition. So the first thing you want to do when you're writing a proof using the contraposition is you want to write the statement in if-then form. That is done for us right here. The next thing you want to do is write the contrapositive of this sentence. So we start with the for all part, so that stays the same. For all real numbers are. And then remember that P implies Q is logically equivalent to the negation of Q implies the negation of P. So here, P is this guy and Q is this guy. So in order to take the contrapositive of this if-then statement, we take the negation of Q. So if R is not irrational, so if R is rational, then R squared is not irrational because we're taking the negation of P. So the negation of irrational is rational. So R squared is rational as well. So now all we have to do is write a direct proof for this sentence right here. And then once we prove the contrapositive, we prove the conditional because the contrapositive is logically equivalent to the conditional. So we can say suppose or assume, I like writing the word suppose. Suppose R is rational. We write the if part of the if-then sentence, and we also include the details here as well. So we could say, suppose R is a real number. R is a real number, and we write the if part of the if-then sentence. So, and R is rational. So rational. The reader might not know what rational means. You don't have to define what a real number is, but you do have to define what rational means. Why? Well, one reason is we're trying to prove that R squared is rational. So we're going to have to reuse the definition of rational later on in our proof when we address R squared. So right now, if we define it at the beginning, we could derive R squared and show that it too is rational. So what is the definition of rational? Some number is rational if there exists integers a and b such that the number is a quotient of a and b is not equal to 0. So we could say by definition of rational, since R is rational, we say R equals a over b, so the quotient of a and b, such that a and b are elements of the set of integers. So now let's introduce R squared. So we can say then R squared equals, since R equals a over b, R squared equals a over b, in parentheses, squared. And that equals a squared over b squared, because when we distribute the exponent to the numerator and the denominator, we get this. And we know that a squared and b squared are elements of the set of integers because integers are closed under multiplication. Because remember, we said that a is an integer, b is an integer, so a squared and b squared must be an integer, because if we multiply integers together, the product is an integer. So a times a, b times b are integers multiplied by each other. So that creates integers, and that's what this part right here means, closed under multiplication. Likewise, if I say closed under addition, that means integers added with other integers create integers. Integers are closed under subtraction means if you subtract integers together, the difference is an integer. Remember that integers are not closed under division, meaning if you divide integers together, that does not create integers always. So integers are not closed under division, but are closed under addition, subtraction, and multiplication. So now what we can do is we can say, I want it to be crystal clear that r squared could be written in this format, where it's some integer over some integer. Over here it's a little messy because it says a squared, b squared, and even though I indicate that a squared and b squared are elements of the set of integers, I want just one variable on top and one variable on the bottom. You could, if you really wanted to, depending on what your professor wants, you could just put a comma right here and say, which is the definition of rational, because we did show that r squared is the quotient of two integers. However, if you want to be really precise, it is optional for you to say something like, let s equals a squared and h equals b squared. So I just chose some random letters, s and h. This means r squared equals s over h, because s equals a squared, h equals b squared, so r squared equals s over h, where s and h are elements of the set of integers. And now we can clearly say which is the definition of rational, because r squared is equal to some integer over another integer. So now, instead of saying thus r squared is rational, thus the then part, because this is a proof by contraposition, we say the whole if-then sentence. So we say, for all real numbers r, if r is rational, then r squared is rational. So we just proved this if-then sentence right here. And because this is the contrapositive of this sentence, if we prove this if-then sentence, then we prove this if-then sentence. So we can show that by saying, therefore, by the contrapositive, because of the contrapositive, because that's proven, we could say if, and then we write the original if-then statement. So we say, therefore, by the contrapositive, for all real numbers r, if r squared is irrational, then r is irrational. And then you could put like a little square right here indicating that you're done writing this proof.